Now, we all work in base 10 quite regularly, so we're quite happy with the columns 1, 10 and 100. And we used to call these, when we were in primary school, hundreds, tens and units. And those of us who got very good would use the thousandth column when we started representing values. And we would use the digits 0, 1, 2, 3, 4, all the way up to 9. So 10 different digits for the fingers on your hand from many, many, many hundreds, thousands of years ago, when doing some commerce of counting how many apples I've got in a basket, or how many pears, bananas, or how many of a quantity I'm selling to another tribe or whoever. Right? And therefore we can do counting. We can start at 0, and of course there'll be 0 in the other columns. If I just remove the thousands for now, we'll stick with hundreds, tens and units, and then we'd start with a 1, then a 2, 3, 4. Of course all of these are 0, but we don't write them, do we? We don't write the leading zeros. So all of these we miss out through convention more than anything, but later on when we see binary work we're going to have to use them. So 0, 1, 2, 3, and then we get up to 9. Oh, let's put that back in a separate colour. So 9, and then once we're finished at this point with 9, then we need to use the other column to indicate that we've got 10 of the items, or one of these, so one of this column and none of these. And then we can continue counting up 1 and 1, etc. 1, 2, and then we have 2 in the tens column, and so on. And when we get up to 99, then at that point, we can then use the third column and 100 and continue counting. But all possible quantities are available because of these digits here on the right hand side. Now the headings are obtained via this, the base heading. I'll use a different colour here, but in fact I'll rub out these parts here and so on. Right, the headings are contained from all bases via 10 to the power 0, 10 to the power 1, 10 to the power 2, and we know we can go on to 10 to the power 3. And we know that anything to the power 0 is 1, 10 to the power 1 is 10, and 100 and 1000. Now, as we go through binary work, we refer back to base 10 a number of times, because obviously that's the number base that students are most happy with. And when we're working with base 16, we'll be converting to base 10 and the values students are happy with again. So I'm going to now look at base 2, so binary representation. And in here we'll start with our headings, 2 to the power 0, just like we do with the tens, 2 to the power 1, 2 to the power 2, 2 to the power 3, and 2 to the power 4. All right? These are the 5 headings that we use in number card, the binary cards that we've seen previously. And underneath these, I'll just calculate the 2 to the power 0 is 1. Well, anything to the power 0 is 1. 2 to the power 1 is 2. This is a 4. This is an 8. And this is a 16. And the digits available to us in base 10 were 0 all the way through to 9, so 1 less than the base heading itself, and with 0 that made 10 possible digits available to us. 0, 1, 2, 3, all the way up to 9. That means 10 possible, 10 different values available to us. With base 2, there are 2 possibilities. This is why it lends itself well to digital technology, a 0 or a 1. And 0 would indicate off, and this would indicate on, this would indicate false, and this would indicate true, this would indicate a south pole, this would indicate a north pole, and later on we'll see another representation of it, which is a capacitor possibly with electrons on the left plate, and this one would be a capacitor. This would be in a memory sticks, flash memory, with electrons populated or charged onto the right plate. So that would be an indication of it. But there's the two possible states. Some students may start talking about quantum computing at a later point, where there's going to be a variety of different states. But with quantum computing, there are those still engineering restrictions on being able to calculate or perform simple operations, and there's news articles on those, and we'll look at those as well in later points. But we've got off-on, we've got magnetic memory, we've got flash memory, hard disk drive. This one will be a Boolean logic, and this would be a circuit. And what I mean by off or on, if I just draw a circuit on the right hand side with a light bulb in, most of the students will have done some sort of electronics, and we'll put a power source, but we'll also have a gate. And if the gate is open, then that indicates a 0. But if I then decide to shut the gate, and well, so if the gate is shut, there we are, there's the gate or the switch, then the light is suddenly on because the circuit then flows. All right, so that is indicated as a 1. So that's used many, many times, and I use that in my terminology with the students. Okay. If I get rid of this circuit, all that information below, we'll just get rid of that just for a second, just so that we can start representing some values using our possible digits of 0 or 1. These are available to us. So I'd start the students counting, and I've got worksheets for this. So 0 would be 0, 0, 0, 0, 0. Now, unlike base 10, we do need to write these values in. Now, the reason for that is they have to have some quantifiable value, and so, because otherwise there could be remnants of this is a gate that's open and it indicates a 1. Then therefore that value becomes a 4. Or this is a 16, and so another value is a 16 plus a 4, so it would be 20 overall. So we've got to switch all values. Let me just put those headings back. We need to switch all values to whatever state they need to be. Right, let's have a look and count up. So the next value will be 16, 0, 0, 0, 0, 1. And the next number will be 2. The next number will be 3. The next number will be a 4, which is a 4. The next number is a 5, which is a 4 and a 1. The next number is a 6, which is a 1, 1, 0. And we build it up that way. I've said that we have all these zeros over here, but I'm not going to draw them in for now, but the worksheet would show how they would need to be inserted into the table. So all these values, and I go down all the way down, and let's go down to the number 30, which is a 6, which is a 16, it's an 8, 16, 8, 24, plus a 4, 28, plus a 2, 30, and that's the number 30. And I'll put the subscript there to say base 2 and base 10, and the final value, 1, 1, 1, 1, 1 in base 2, which is 31 in base 10. I'm just going to get rid of that symbol that I just drew in because I don't want everyone thinking that that's a negative value. All right, so that's the number 31. The binary cards video shows how all these bit patterns are unique for any value. So this number of 6 here from base 10 cannot be represented any other way in binary other than a 0 in the 16s column, a 0 in the 8s column, 4, 2 and a 1. So this unique bit pattern always represents the value 6, which is useful because in all machines then, or all devices or components that are communicated with, then the value 6 will always have a 1 in this position and a 1 in this position and zeros in all other positions. And this is just 5 bits, but if it was an 8-bit machine, then it would have preceding zeros at this end to 8 bits or 16 bits, 32 bits, or nowadays 64-bit operating systems, all the powers of 2, of course. Which brings us on to the next. So if we start with 1, 2, 4, 8, 16, 32, all numbers that students will have met before, so that's 128. Now in this particular page, we've now got 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. 8 bits indicate equals 1 byte, and we're quite happy with that. 1,000 bytes equals 1 kilobyte. You'll be familiar with that from kilometers and kilometers or kilometers. Kilometers probably the best because the meter is the unit with kilo before it. So kilometers or as opposed to kilometers. Kilo is the unit that indicates the 1,000. And then we go on to megabytes and so on. This number here, in fact, this 1,000 is in fact in computing 1,024 bytes. So maybe I should say at this point that that is about 1 kilobyte, 1,000 bytes. But 1,024 bytes equals 1 kilobyte, 1 KB. And then 1,024 KB equals 1 megabyte, and then from there we go on to gigabytes, terabytes, and all the others, petabytes, yottabytes, and so on. That's for them to fill out and for them to maybe research, or some of the textbooks have those tables in which have the unit all the way up to the yottabyte. So the yottabyte, which is on the GCSE curriculum, which would store something like 6 billion, maybe 67 billion years of video of all people's lives or something like that. Alright, so 67 billion years worth of video on my 1 yottabyte memory stick, which would be a very big memory stick indeed, and it isn't quite engineered possible at this point. But nonetheless, all the others, megabytes, kilobytes, and the bytes, the 8 bits, are possible, and that's the bit that we're going to be using at present. So, if I just take that back to, I would say to the students, right, let's represent a few numbers. Let's have a look at the number, well, just pick a few numbers. So 27, we'll pick 83, and we maybe pick the number 167. Let's see what 167 gives. So just throwing out a few numbers so that they look from the left-hand side, from this position here, and work across, and just do some mathematics in that they would need to just say at this point, let's have a look. Let's have a look. So the number 27 requires no 128. It doesn't even require that, and it doesn't require that. But it will require a 16. And it leaves, because 27 minus 16 equals 11. So we're now looking at this position here. Does it need an 8? So, yes, it does need an 8. And we're now left with 3. So that doesn't need a 4, but it needs a 2 and it needs a 1. So 27 is that pattern. And I'd carry on with the students and do a few more of these. 83, and it's a good way of them just getting their maths working to be able to do some of these. So 83, 64. So we're talking about 83 minus 64. We're left with now, we're left with 19. Not many of them come up with that immediately, but we're now left with 19. So that's no 32s. It's a 16, which leaves a 3, and some will already be at this point where they're quite happy to write those out. And if I bring that down, and then we will have 167 where we've got a 128. So 167 minus 128 gives us 39. Oh, sorry, equals 39. So we don't need a 64, but we need a 32. We don't then need a 16 because we've got 7 left. So 39 minus 32 equals 7. So now I'm looking into this position. Do I need a 16? No, I don't. So no 16s. Do I need an 8 to make this 7? No, I don't. Do I need a 4? Yes, I do. Do I need a 2? Yes, and yes. And 4, 2 and 1 comes to 7. So we'll check that. And what we'll see, in fact, some of these headings are quite useful to work with. 128 plus 32 equals 160. You'll see that 64 plus 16 equals 80. You'll see that 32 plus 8 equals 40. And further on, when we look at 8 and 2 make 10, 4 and 1 make 5. So all fairly nice to work with after a while. So if we just work there, so they can work along the headings, although the more formal approach for storing these values is to continual division by 2. So, and this then works with any number base as well. Continual division. So if I start with the number 167 and divide, oh, in fact, let's do a smaller value just to. So we start with 27, for example. 2 into 27 goes 13 and its remainder 1. Most students can halve quite easily. 2 into 13 is 6, remainder 1. 2's into 6 is a nice one because it goes in exactly. So it's 3, remainder 0. Don't forget to write the remainder. 2's into 3 go run 1, remainder 1. At that point you can stop, but some textbooks like to go this 2 into 1. Now 2 into 1 goes no times and remainder 1. And then you will read the value from the bottom upwards, and we'll see that 27 base 10 equals, I'm going to read from the bottom, 0, 1, 1. So 0, 1, 1, and then 0, 1, 1. So it's a nice repetitive number, this one, 0, 1, 1. Tell students, always check this, so you'll remember that your headings are 1, 2, 4, 8, 16, 32, so that's none. 16 plus an 8, 24, plus the 3, 27, so we've got that right. So I would set a few of those then just for the students to do this continual division by 2 at this point to get the remainders on the right hand side. So they work well, they will work well through that, and it's just a good way of checking. One, they can divide by 2, but also that they can check their work afterwards. So this final check to look along the headings to see what's there is again very useful. But it works for all number bases. So when we will talk about hexadecimal at a later point, they can always work with those headings.